okay?
Okay.
It runs. Perfect. So, welcome to our lecture, Fluid Energy Machines, Chapter 4. Today, I will teach you something about wind turbines. And if you look at Central Europe and Germany, if you look outside today, it's not a real good weather. It's windy, it's rainy, and more or less in Europe, this is somehow normal. We have an average wind speed of about 4 to, let's say, 10 meters per second. And if we look in Germany, we have some areas where we over 4 to 5 meters per second, and even some areas where we have over 5 meters per second. So this wind velocity is quite suitable for wind turbines. We can use them, they will work, they are efficient. So yeah, I think wind velocities in Europe and Germany are quite well for this type of energy production. Let's have a small look at the development of wind turbines during the last years. This is a nice picture of the Netherlands. Yeah, you can see it here is the seaside, the North Sea. We have a dam, and if you have been to the Netherlands, you know it's a really flat country. And if you look closely, you can even see that the water line is over the country. Yeah, over the normal level of the country. So the people in Netherlands always had this really flat country, this country where the level of the land is a bit below the seaside. And here you can see some wind turbines. You can see small wind turbines. They're somehow older. They are about 300 kilowatts, and they have a small rotor diameter of about 25 and a height of 45 meters. And behind these small, older wind turbines, you can see some modern turbines here. You can even see the construction site. They built a small construction site, and they have some cranes where they're still under construction. And these wind turbines have about 7.5 megawatts, 7,500 kilowatts. They are really high, 127 meters rotor diameter and a height of about 200 meters. And nowadays you see a lot of these really big windmills, and the construction is really fast. I see it often here in this area when a new wind turbine is built, they can build it in weeks. Yeah, it's really fast. So I want to mention that our school, the HTW SAR, has a really close relationship to wind energy. We've been pioneers. We've been pioneers in wind energy in the early 1990s because some students and a professor, Mr. Friedrich Klinger, built a startup where they invented one of the most wind turbines, and they made it really clever. They invented a gearless wind turbine. I will show you what this means later, but we still have a good relationship to the company Wenses. Nowadays, it's one of the world leading companies in wind turbine, and we have a production site here in Neunkirchen. From time to time, I visited together with the students, and they have also a big, let's say, sister company in China. It's a Goldwind, and yeah, and many students come from many students who worked or did the internship at Wenses. They come to our lectures, and I can also tell you, I have still a close relationship to Mr. Klinger. He is nowadays he is over 80. He's a really really old person, but he's still fit and he still works. Yeah. Okay. Yeah. So if you are interested in a job in wind energy, you can get contact to the Wenses, and or if you want to do a bachelor thesis or master thesis, you can ask there for a job. Okay, but before we come to this technical points, we have to look a bit at the theory of wind turbines. And in general, if you want to use a wind turbine, what is important? Important is the energy that is inside the wind. Yeah, here I show you a simple sketch. Here's our wind turbine. Here is the area of the rotor, and the area of the rotor gives us a hint about the air that hits the rotor. And you can only get the air, you can only get the energy that is inside the air, and the total energy that is inside this volume of air can be calculated by the equation energy equals 1 divided by 2, so half times mass times squared velocity. Yeah, velocity of the wind. Often you see the symbol for wind as W or V or U. In most cases, we now use the C for these fluid energy machines. And you can calculate another really important formula is the power. Power is very much the same as the energy, but it's derived after time. And you can also calculate the mass flow. And I always tell you that you should prepare a formula sheet for yourself. And of course, these formulas are all really important for your formula sheet. Yeah, here the mass flow, it's area times density times velocity of the wind. So that's you can't get more power from the wind than this because there's no more energy inside this wind volume. Okay, and why do I? Another thing I want to mention is here in fluid energy machines, we have to have a close look at the temperatures. Why do I explain this to you? Because we had together with Professor Klinger and his company, Innowind GmbH, we had a really big project about heat transfer. And now you ask me, why heat transfer? This is we talk about windmills. Why do we have to know something about heat transfer? But heat transfer is also really important for the construction of wind turbines because these big wind turbines, they produce a lot of heat. Yeah, they have a big generator and you have to cool it. So here's a small mistake. Should be written with it's a German writing. It has to be written with C. You have conduction. Conduction means the heat goes through solid bodies. We have convection. Convection means the heat is transported through a fluid, water or air. And we have radiation. Okay, I don't want to go too much deep into the theory of heat and mass transfer or thermodynamics. I just want to mention the three main principles. And where do I need these principles? I told you wind energy has a lot to do with heat transfer, with cooling, because that is always a problem. In former times or at competitor windmills, they have also, if the windmill has a gear, yeah, a gear inside, this is also always a big problem, yeah. But these new windmill types from Wences or from Mr. Klinger do not have any gears. They're gearless, so a lot they don't have. They're really stable and don't get these problems with the gear because they don't have it. But they have a big generator, and the generator is the best position of the generator is outside of the windmill, because then you can get air from the surrounding that can pass through the generator, and it can cool it down, and then you get some cooling of the generator. On the other side, there are also this technique of active cooling. Active cooling is like a climate system. You have here also again the generator, but you have an active system, a pump and a fluid fluid heat conductor, and you need some fluid to cool it down, and of course this costs energy. So this active cooling is much more expensive. It's like a climate system. It can be damaged, and of course you have to pay for it, and you have to pay for the electric energy. So this passive cooling is much, let's say cooler, the better technique, because it's less expensive. Okay, and we had a big project about this. We made some theses about it, and we wrote a lot of articles about it. It's a quite interesting thing. Okay, how does a windmill look? Here we have a sketch of a windmill, and now, if you remember the exam I showed you before, there was a question exactly where I asked you this, how to paint a windmill, yeah? So maybe let's have a look. Yeah, I see. I'm sorry, unfortunately, it's written in Germany. What I want to do, I will translate it. Yeah, I will add some translations here on this slide, and now I translate it. But maybe you can learn a bit German here, but I will add it. Yeah, this is the tower of the windmill. We have here our concrete, and to stabilize the windmill, we need some conduction to the power net. Yeah? And we have a generator here, generator that produces electricity. And of course, this, you can imagine, it's a big generator. This will also produce a lot of heat. Yeah? We have also some electric circuits that also produce heat. We have a gear here. This is a kind of bit older. We have a brake. And of course, this gear also produces heat. But with a gearless windmill, you don't need this gear. And that's also always the better version, yeah, because you have also wear in the gear. Okay, and here is a nose and tip. Okay, so let's have a short historical overview over the windmills. Windmill is a really old technique. Yeah, we have these windmills here. You see a picture here in it's an old Saudi Arabian windmill. Yeah, you have it. It's like a tower, and this windmill were used for milling of corn. Yeah, and here you see some plates, and the plates were hit by the wind, and then um, the milling works. This is also a really old picture, 200 years maybe old, and it's 150, and it's an old windmill. It's also a vertical windmill in China. Okay, here we can see some newer windmills. Yeah, and many of these windmills were located in the Netherlands. They have a really old tradition with windmills, and it depends on the philosophy and of the flatland. They can use the wind really good. And in former times in the Netherlands, the windmills were used to grain corn, and they were also used to for pumping. Yeah, they used it to pump the water back over the dam, yeah, to get their land dry. Yeah. Okay, here the so-called box windmill from the 12th century. The house was built that it can be rotated here on the axis. It was quite more or less, was more or less a modern windmill. Then we have this kind of tower windmill from the 14th century and a jig windmill from the 15th century. So you see, this technique is quite old. It's not really a new technique. Here are some parts, some mills from the 16th century. Yeah, this is a bit like a house here, and it was also built to rotate it. Yeah, pile truck mill, or a modern gallery windmill from the Netherlands. Yeah, that's the setup of a historic windmill, more or less. It looks a bit like a house, like a barn, and inside is a gear. It's really similar to modern windmills, and more or less, of course, the gear was not used to produce electricity. It was used to grain some corn. Here you can see a milestone, or it was used for pumping. And to this better design of the windmill, they were able to rotate it, to rotate it into the wind direction to get most of the power. Okay, maybe even you see here, this is interesting. They had even a crane where they can push up, where they can push up all the bags and lift them to the milestone. Here you can see modern windmills, and this quite old picture. We always had it to explain that you can use not only today, nowadays we have in most cases our 3 plates. I think all the windmills now have 3 plates, but it's not necessarily that you have the 3 plates. You can have also less plates. Yeah, you can have maybe 2 plates or 1 plate. That works. Yeah, and in former times they did a lot of experiments. In the 1980s or 90s, they made a lot of experiments. They used 2 plates, 1 plate, and at least 3 plates. Okay, they even had more plates, but more plates are not really efficient. Yeah, I will explain you why. Okay, and here we have a vertical axis windmill. Yeah, we have here an axis in the middle. We have 2 plates at the side, and here again 2 plates at the side of the axis. And these windmills are not really common. Yeah, you don't see them too often, but they have big advantages. Yeah, for example, you can have the generator here just on the ground. Yeah, that makes it much more easy for maintenance, for example. They're not so efficient as the normal windmills we know. Yeah, and I also want to mention, we just finished a PhD thesis of a student of mine, and he did his PhD about this vertical axis windmills. So there's still research in this field and a lot of interesting topics. Okay, here you see a windmill with a vertical axis. Yeah, you have here a vertical axis in the middle. It's the so-called Savonius rotor, and the wind comes from the side. It rotates the Savonius rotor, and it looks like this, and you can have different types of Savonius rotors. You can have this type, and you can have this type. It's open in the middle. It's closed in the middle. It's a bit more easy to produce this, and they can also sometimes they look really strange. For example, you can build it that these blades are a bit rotated about the center, but it works. And another type of this rotor that is really common is here. It looks like small cups or small spoons. And this windmill is really often used, for example, if you, maybe for climate system of houses, if you want to measure the wind and you have to have a smart house, you want to automate something, then you often use this type of small windmill for measurements of the wind velocities. Okay, here I want to show you also a bit about history. I told you windmilling is not really new. It's an old technique, and even it was even developed in the last century. In the beginning of the last century, they had some windmills. I've been to a location in Denmark where they had a windmill in the 1930s, and it really worked. Yeah, but then it was not so common. Windmilling was not so common in the mid of the last century. They used more coal power plant or nuclear power plants, but it existed. Yeah? And there's a famous scientist called Albert Bates. He died in 1968, and he worked on many theory and on the background of windmilling. He also published a lot in windmilling, and here you can see him in front of his wind tunnel. He made also a lot of experience in um, wind energy. Yeah, if you look closely at this picture, you see here a kind of wing. It's a NACA profile, maybe of an airplane or of a windmill, and he checked the design. Yeah, this design is really difficult, plate design, and he checked it with his wind tunnel equipment. And what he did, he founded a really familiar formula. And this is also something that must be on your formula sheet. It is really important. It is the maximum efficiency. It's a called Bates factor. It's 16 divided by 27, or let's say 0.59. And this is the maximum efficiency a windmill can get. It can never be higher than this. I want to explain you a bit why and how he made this, how he proved this. Okay, and that's also something I want to tell you. Normally, when you are here in Germany or when we can meet at the HTW, it is I always go with you together to our wind tunnel. We have this laboratory here at the campus Altsaarbrücken, and normally I do a lot of experimental work together with the students. I do experiments, I do research, and it's always really interesting to I think for the students to work there in the lab. And normally, if you come to us from Finland or other countries, you can do an internship there, or you can do some experiments there or thesis. This is always really, I think, a good laboratory. Yeah, it's good to work there. Yeah, you can have computers for simulation. We have possibilities to sit there and to work, to discuss. And we also do experiments with windmills there. We can build small windmills, put it inside, and we can get about 9 meters per second of wind speed in this tunnel. And this is exactly what we need. If you remember here, our first slide here. Let's skip to the first slide. Yeah. So round about 9 meters is quite good, yeah, to make experiments on your windmill. Okay. So that's how we work. We can, no, we can build models. We can build them up. We have a lot of possibilities in 3D printing. We can do. We have a lot of possibilities in metal forming here. We can do digital twins. Yeah, we can build up a kind of digital model, and we can also make computational fluid dynamics simulations in this lab, and we can measure CP numbers. Yeah, please remember CP here, maximum CP. Yeah, and I'm a bit shy. I don't want to click here because I know from former times when I click here, it is not so good. It can cause some problems now. I don't want to do it, but you can do it on your own. You can look at the slides. You can go to the QR code with your smartphone here and see the movie, or you can just click the link in the slides, and then you can watch an experiment where our windmill rotates. Okay, then we have another interesting experiment, and it's so-called BOS. It's background-oriented Schlieren method, and we use this BOS method for production of turbulence. You can't, if you just look at the windmill, it's not possible to see the fluid flow. That's often something I try to explain to you. If we have a pump with water, we can't see the fluid flow. We can't look inside. Or if we have a windmill and we look at the windmill, we don't see the fluid flow. Yeah, the air is invincible. We can't look at it. Yeah? And this makes it often a bit difficult to make measurements or to calculate efficiency because it's invincible. You don't see anything. And we built up a method, a so-called background-oriented Schlieren method, and it depends on a software filter of a camera. And with this filter, we try to visualize the turbulence behind wind. Yeah. Here, yeah, again, here I don't want to click on it because you can click on it on your own afterwards. And here you see some hot air is coming out of this nozzle, and we made this software filter. You can see the laptop, and here you also can see on the movie the nozzle, but you will also see the fluid flow of the hot air. This is done by a software filter. Yeah. So in our lab, we not only build up windmills or did something in steel and iron. Yeah, we also do a lot in the field of programming of software filters or in automatization of this tunnel. Okay, how did Albert build the proof of the maximum efficiency? Yeah, how has he made it? Yeah, and here you can see a formula. It's a pressure difference, velocity, and area, and it's a power. And he just set in here the power difference and made this mathematical calculation. And then he got to this solution that the efficiency of a windmill can never be higher than 16 divided by 27. Okay, what does this mean to us? We can now make measurements of all the different wind turbines. For example, I showed you in former times there have been one-bladed rotors, two-bladed rotors, three-bladed rotors. But if you look at the efficiency curves, you see, yeah, the maximum efficiency is not really much higher if you use more blades. And even if you use 4 blades, blades are really expensive, they're really big. It doesn't help you a lot in efficiency. Here you see the maximum efficiency curve. It goes to this value, to this maximum value of 5.9. And here you can see some smaller windmills. These are older windmills, a Dutch windmill, or in history there was also a great usage of windmills in Westerns. So you maybe know it from Wild West movies where they used these windmills. They were, in most cases, they were used for pumping of water. And here you see our Savonius rotor. Let's look at the principles of drag and lift and how does the windmills work. And again, a small hint from my side. Remember the exam. This was also a question in the exam. So this is how I think you can't paint this on your formula sheet, but you have to understand it somehow. But I think if I explain it once or twice and you know it, how it works, I think you should be able to remember it somehow. Yeah. Okay, we have two main principles. We have a resistance principle. Here we have our flat plate. The air comes from this side. It hits the flat plate. It goes around the plate. You have a swirl in the back. And if you have swirls here, you have lower pressures at the back. You have higher pressures in the front. And you push this blade and you this is a principle how windmills can work. For example, if you look back at this small windmill here, the movies are always a bit here. This is the best example. This with the spoons is the best example for a resistant windmill. Okay, let's go back. So, and the second big principle you can use is the buoyancy principle. With buoyancy, you have also wing. Yeah, here you can see the wing. We have a wind velocity. The wind hits the wing. It causes a drag force and it causes a lift force. Yeah, you can, the wind will lift up this wing and then you can get energy, then you can write rotation. So in all modern wind turbines, you use the buoyancy principle. Yeah, you do not use the resistance principle. It's important. Yeah, here are some examples again. The first windmill that was used for electric purpose was built in Scotland. Yeah, there you have high wind velocities, and it was a track principle. Yeah, he used this here, these spoons, these big spoons, to produce rotation. And here's a modern Wenses wind turbine with about 2.5 megawatt. Yeah, it's a standard. It's not really big. It's a standard windmill, and they use a buoyancy principle as a lift principle. And this is a nice picture. You can look inside here. You see the generator. It's located outside. This is a really cool design. We also did a lot of, we worked a lot on this kind of designs. We make safety simulation, or we made a lot of design experiments with this generator types here. And we had a big research project for this. Here you can see electric circuits inside, generators. Okay. And you can also see there's no active cooling system. It has a passive cooling system. This is much cheaper and much more easy and much more, much better than an active system. Okay, how does the fluid act on the wing? If we look on our turbine axis here, here's the turbine axis, and we have the wind velocity. Wind velocity is always has always a symbol C, and this is a rotation velocity U. And now, if you know something about vector mathematics, you can calculate the resulting velocity W by the vector of the wind C and the vector of the rotation velocity of your windmill. Here you can see the definition of the rotation energy. And these velocity triangles, let's call them velocity triangles, they are somehow a bit difficult to calculate. Yeah, you have to calculate them for every position on the wing, because at every different position, the rotation velocity is kind of different. Okay, how can we calculate the available power of the wind turbine? Here we have our plate, we have our force. We can calculate the area of the rotor by this formulation. That's also make a cross here. You will need this formulation. And if the wind hits the windmill, you spread the streamline. So after the windmill, you have turbulences, you have a higher diameter here of this area. And of course, because of this, you will get a lower velocity. Let's look closely, a bit more closely on what happens. You have here your stream tube. That's the energy that will hit the windmill. You have a pressure. That's normally your air pressure, 1 bar, 1 atmosphere. And before here this rotor plate, the pressure gets higher and higher, but the velocity gets lower. The velocity gets lower because why is the velocity behind the windmill lower? Because you lose some energy. Some energy will be used here to produce electricity. So you take some energy from the wind. Yeah. And also the pressure is higher here in front of the windmill, but below the windmill, it will go down, it will be lower. But if you come far away from the mill, you see it goes again to your atmospheric pressure. Why? Because of course the air will also go around. Yeah, if you have a high pressure here, low pressure here, it will go around the windmill, and you will get again a high pressure at the back. Okay, here again is the same picture. You have the plate, you have the atmospheric power, you have a higher power here, a higher pressure here, a lower pressure here, and you get back to the atmospheric pressure if you're far away from the windmill. But velocity will be higher here, and velocity will lower behind the windmill because you take back the energy. And you can make an energy balance really similar to our Bernoulli's law, but it is not Bernoulli's law, but it looks a bit similar. You have your here your atmospheric pressure, and you have here your kinetic energy, yeah, and this should be the same as here. Okay. Again, the same picture, yeah, same picture. You have here your rotor, you have your area, you have you can calculate the kinetic energy of the wind. That's the same equation as on the second slide of this presentation. Kinetic energy is always have to keep in mind. You have to know it, and you can also calculate the power. Okay, yeah, similar formula. I think we can go a bit fast over it. You can also calculate the thrust, the force on the wings, and you simply calculate by the pressure difference times the area. Yeah, you remember you had a higher area in front of your wing, a lower pressure behind, and if you calculate the difference, you get the force that acts on your wing. Okay, yeah, that's again some interesting topic. The wind flow, that's a yeah, that's something that is currently a really common topic in research, and it is about the profile of the countryside and of the locations of the windmills, and it is also about, for example, forests or or here trees. If you have some trees, they influence the efficiency a lot. They influence the wind flow a lot. Yeah. For example, if you have a tree here, height of the tree, 5 times before the tree, you have turbulence. So this is not a good position to play the windmill. And 10 to 15 times after the trees, you have also some swirls. So the efficiency is much lower. And currently, we want to do PhD thesis together with students, with Mr. Johannes König, and he wants to do his PhD about the influence of forests and the influence of terrain of the mountains on the windmills. Now let's see if we can do it. Okay, how can you? I showed you this more or less simplified sketches, but you can imagine in reality it's much more complicated. Turbulence is more complicated, and also my staff member Daniel Leser-Pfeffermann, who did also his PhD thesis in turbulence. This turbulence calculation is really sophisticated, but you can imagine normally the flow behind of the wind doesn't look so ideal as I have explained to you at the beginning of this presentation. It is, if you really want to make design, it's much more complicated, of course. Here you can see a windmill model, so-called digital twin. You see here a person. It's about 80 meters high, 80 meters of diameter. And here I plotted some turbulence behavior. Yeah, it looks much more strange than this simplified wind tube. And I added some more pictures. And behind this windmill, you get a swirl that looks more or less like this, like a spring. It looks a bit like a spring. And what we did, we also measured this swirls, and we measured it with a small airplane that we took and we fly through the windmill, and then we get some information of the swirls. Okay, here we have the that's another problem. We have the boundary layer, we have the ground of the forest or of rocks or of grasses, and you get some turbulence in the, yes, it was our dog. He wants to have some breakfast, I think. Okay, here you see the swirls, turbulence, the boundary layers, and the velocity rises with the square of the height. So in higher altitudes, you have much higher wind velocities. Okay, well, that's also CP, not so important. I also want to mention the blade element method. That's something I explained you before. We have these triangles. We have this velocity triangles. We have this rotation speeds, and these U values, these rotation speeds, they get higher and higher if you go into higher radiuses. If you're here in a small radius, you have lower U values, and if you go to higher radiuses, you have higher U values, U velocities, and so you need other velocity triangles. And to fulfill this, you have to rotate the plate. Maybe look here slightly at this wing. You have to rotate the plate a bit to fulfill this velocity triangle, because the C value is more or less always constant. Again, here are our principles. I explained it. And let me mention, it's difficult to calculate all the forces on the plates. And I just want to mention there are, of course, you don't do it with a sheet of paper and pencil nowadays. There are a lot of good advanced simulation programs, for example, like Bladed or Simpac or Adams, and you can use them to make sophisticated design calculations of your windmill. I use on this workbench really much for the design of the windmills. Okay, let's skip this and come to the end. When you make your simulation of the windmill, you get so-called performance curves. You have a diagram where you paint the power over the rotation number, and here you can get complicated performance curves. That is important point. I mentioned this BOS efficiency, but efficiency really much depends on rotation. Yeah, it depends on how fast your plate is, and depending on the rotation number of the plate, your efficiency can also change. Yeah, and you can get an optimum performance. So you always have to work. If you want to use your windmill, you have to have an optimal performance curve. Yeah, if you work in a non-optimal mode, you don't get so much energy and performance from your windmill. Okay. Of course, your optimum depends really much on the pitching. Yeah, you can rotate the plates a bit to fulfill the demands of the wind velocity, to get your triangles right, and then you can change the position on this efficiency curve a bit by rotating of the plates. Yeah? How can the plates be rotated? Maybe I go a bit back to this picture. Here, you can see here. Yeah, it's a small picture. I know. I was often there in this company, and it's better if I show it on a real machine. But here is kind of motor, electric device, and you have here like a rubber band that is that goes around our wing. And now if you rotate, if you pull this rubber band, you can rotate this big wing. It's maybe I try to get some better photos. Yeah. Okay. Switch to the. Yeah. Good. Here is it again. The same picture. Yeah. You have here. This is a wing. You must rotate it. You must pitch it to fulfill the demands of the wind, and also to get less mechanical load. Yeah. To break the windmill a bit. And here is our engine. You pull this rubber band, then you can pitch the blade. Yeah. Another important point is here this azimuth bearings, the main bearings, and it is also possible to rotate the whole windmill to the direction of the wind. And the windmills, they do it by their own. Yeah, they are smart today. Yeah, they can measure all the wind velocities by themselves, and they can do all this rotation work by themselves nowadays. Okay, that's also something I want to mention. To design a windmill, you need CFD simulation, you need multiple body simulations, you need finite element analysis. Here you can see, I can't teach you now in this seminar all these topics. Yeah, I can't teach you CFD now. I can't teach you finite element, but you have a small impression. If you want to calculate any frictions or tensions inside these metal parts, you need finite element simulation. Okay, here again, that's something I mentioned. You can have a gear inside. Here you see the gear, but that's more an older construction. And if you have a look at these modern designs, they are gearless, they're more simple, they're much better to use. It's a direct drive. Okay, I think more or less here's something about simulation. I don't want to mention this too much, this simulation stuff, and I think we should finish this lecture here. Okay, and I think you can stop the movie now, Mr. Luther. Hello?